deal with the units of measurement, it's very important to understand available units to engineers and to scientists, as well as how to convert them. Often you end up converting from one system to another system or within the system, so it's rather important to learn and feel very comfortable doing it. Right off the bat, we have four fundamental physical quantities. These are the major quantities, starting from the length, and then mass, time, and force. Many of other quantities have been driven from these four main quantities. For example, you talk about the acceleration or speed, so it deals with, for example, the length as well as the time. Or you talk about the pressure, so it deals with the force in the air divided by the area, or force per area. So if you understand these four fundamental and main quantities, you can also drive them to many other used quantities by engineers. For example, the second Newton's law, force equal to mass multiply by acceleration. So this is a simple equation. Can you get to the relation between these? So force, let's say for example the unit in SI system is Newton, mass is kilogram, and acceleration is meter per square seconds. So now this relate the most important relationship between time, force, mass, and the length. So all these four can be seen in this. We have the mass, we have the time, we have the distance, and we have the force. So in total we have two major systems. So one is IS, International System. IS is the French System International, and the other one is the US customary system. It's a British system, and many of us we are familiar. In North America it's very common. In Europe as well as in Asia, they're using still SI system. So for you, when you graduate and you perhaps may work overseas, you should feel very comfortable using the international system, which is commonly practiced outside of North America. Let me start by introducing those major four quantities in these two units. Length in SI is per meter. 1 meter is 100 centimeters, and 1 centimeter is 10 millimeter. You can go in more divided. You can go to up to micron or nanometer, but most commonly we have meter, centimeter, and millimeter. Time in both units are second. Mass in SI system is per kilogram, and the force it's per Newton. So Newton is kilogram meter second square, and obviously this is driven from the second Newton's law. In foot-pound or US system, length is per foot. 1 foot is 12 inches. Time, second, as I mentioned in both units. Mass is, the unit is called slog, and I know it's not very commonly used, and it's a kind of misconception in North America. When you go to grocery, you want to buy like a tomatoes, you say 2 pounds of tomatoes. But truly pound, although it's been used incorrectly as a measure meant for mass, truly it is a unit of force. Slog is the unit for the mass in foot-pound system, and pound is the unit for the force. We will talk about this in detail, and there will be a video at the very end of this module dealing with the difference between the mass versus the weight. Let's start with some also basic conversion. So 1 ounce, using ounce again in foot-pound system, is 28.34 grams. When we are in this topic, we have the ounce, which is 28.3 grams, and then we have troy ounce, which is often used for precious metal, and that is a very different. It's 31.1 gram. Usually for 99% of the cases when you use an ounce of anything, it is 28.34 grams. 1 pound is 16 ounces. So obviously from now you can do a simple math and you know 1 pound how many grams it is. So it's 28.349 multiplied by 16, which is 453.59 grams. Next is a kilogram. Obviously kilogram, by the same conversion, you can divide 1,000 grams by 28.1,000 gram divided by 28 by this number, and this, which is obviously not a integer number, is how many ounces are in 1 kilogram. So now simply can connect these two together and you realize that 1 pound is 2.204. 1 kilogram is 2.204 pounds. So that's the simple conversion. How many pound is 1 kilogram? Well, in that case, this number, so you go and put decimal here, so is 0.435. Obviously pound is, in this particular case, pound is smaller than kilogram. Once again, this is a misconception in the physics and outside of the physics. Outside of the physics, pound is used for the measuring mass. Inside physics, pound is used for measuring force. So what I said here is mostly when we are dealing with outside of the physics. 1 inch is 2.54, and that there is no more than this. Has 3 significant figure. It's bang on, obviously. So or you can say 1 inch is 25.4 millimeter. So common conversions, it's very important for students to understand this conversion. So we talk about 1 foot is 12 inches and 1 inch is 25.4 millimeter or 2.54 centimeter. So simple conversion, 1 foot is 0.3048 meter. So 1 meter is 100 centimeter. You can simply divide 100 by 2.54 and you realize 1 meter is how many inches, and then you divide that number by 12. So the answer would be 1 foot is almost a little more than well, is less than 1/3 of a meter. Very, very important conversion. This is really important conversion of pound in physics to Newton. I go over a little detail and show you how this conversion happens. I really encourage my students to always, from first to fourth year, to remember not only to memorize this conversion, but also to know how to drive it. And the reason is because now, when you want to go to the conversion of the pressure, then you have to use the same concept. Here is the simple calculation. So the calculation here is 1 pound, obviously, is pound force. So you want to convert that from pound force to Newton, and we know the Newton is meter meter divided by square second multiplied by mass, MA. So the conversion starts from pound multiplied by this is the acceleration of the gravity, g, and then you divide it by the value that we already represented, which is 1 meter, the conversion of meter per foot. So in this case, you divide it by this value because obviously meter is larger than foot, and you will get this value here. So 32.174. So this is a foot pound square seconds. And then the next step is you converting the pound to the kilogram. So 1 pound, remember that is 0.453 kilogram. So all you need to do here is you converting this value multiply by this value, and the answer would be 4.448. So 1 pound force is 4.48 Newton. 1 Newton is 1 divided by 4.448. So these are two simple things. So this represent the gravity, the acceleration in pound, foot-pound per square seconds, and this is the conversion of the pound per Newton. So whenever you want to see what is the G, 9.8, it's in SI in foot-pound system. It is 32.17. So let me just delete these ones. Okay. So the next, we have an example. So I would like you work on this. So we now talk about the torque. You have heard about this car, this transmission has this much torque. So torque often in North America is inch-pound. So this is the inch-pound. If you want to convert the inch-pound, the torque from foot-pound to SI system, you should use what we already talked here. So convert a torque value of 47.0 inch-pound into a SI system. I want to pause here for a few minutes, let you guys do it, but just give you a little hint. The first step for you is to realize, so what is the torque unit in SI system? So it's a combine of two units, is inch pound, and this is the pound force. So therefore in SI system, this is the length is meter, and this is the force is Newton. So when you talk about the torque, torque has the same unit as work. So it's force multiplied by the distance. Therefore, you need to convert that from inch pound to Newton meter. I give you a few minutes and I will come back and we share the answers with you. Okay, did you get the answer? Do you need more time? If you do need more time, you can pause. Otherwise, I go ahead and I tell you the answer. So, inch. What is the relation between inch and a meter? 1 inch is 25.4 millimeter or 2.54 centimeter. 1 meter is 100 centimeter. So if you want to convert that, obviously 1 inch is 2.54 divided by 100 meters. On the other hand, you have the simple conversion of pound force to Newton. So in this case, all you need to do is simply you multiply this value by 4.482. Don't forget, when you go from a bigger value to smaller value, you always multiply. When you go from smaller to larger, you divide. If I want to convert inch to meter, 1 inch is much smaller than a meter, so the value is going to be smaller than 1, the conversion factor. When you are converting foot pound to Newton, Newton is smaller than foot pound, or foot pound is larger than Newton, then you multiply. The answer is 5.31 so on Newton meter, and so we have to respect the significant figures. So here we have 3 significant figures, then we have to have also 3 significant figures, and the round number is 5.31 Newton meter. I'm sure you all have got the same answer. If not, do a little practice and I'm sure you will get it eventually. So let's have a little bit more kind of complex conversion. So a boy mass is 3.5 slug. Don't forget, now we are in the domain of physics and statics. A slug is the unit of mass in British or American system. The question is asking, if a boy weighs 3.5 slugs, what is the weight of the boy in SI system? There are 2 ways to solve this problem. Method 1, go step by step using the most fundamental law that correlating those 4 quantities, which is the Newton's second law, F equal to ma. So force equal to 3.5, that's the mass, multiplied by conversion of the gravity acceleration in foot pound, which is 32 something we found already. So the answer is the boy weight is 112.65 pound force. In a sense, in reality, so this is the actual the weight of the boy per pound, but don't forget, pound is only the unit of mass outside of the domain of statics and physics. So you need to do another conversion, and the conversion is, you want to say what is this force in Newton. So we know the conversion of 4.448. So the boy's weight is 501.057 Newton. So this is actually the weight of the boy. So this is one way to calculate that. The other way, which is a kind of shortcut, is we do a simple conversion. We know that slug was about 14 kilogram. So you do 35 slugs is multiplied by the value. You can go back, and if you want me here, right here. So one slug is 14.5938. So you convert that. You find the mass of the boy is 51.078. So this is the mass of the boy. You want to see the weight of the boy. Obviously, you multiply that by the gravity acceleration, which is 9.8, and the answer is pretty much the same. So you can see there's a little difference here. The reason is we have some rounding, and it's, if you want to round this to 4 significant figure, so you you get here 501.08, and this is, you get 501.06. A little bit difference. It comes because of the rounding here and the rounding here. I hope this explains both methods are correct. I like the first one a little better because it's more fundamentally go step by step. Few things that you have to respect. So for these units, we don't use plurals. So we don't say 5 kilograms, it's 5 kilogram. Or we don't say this is 200 centimeter, not centimeters. The units, you separate them by a dot, like you can see that here. So you make them by this dot to distinguish. Most units are lowercase, like a grams, like a centimeter, like a foot, but there are some exceptions, including newtons, including Pascal, including mega, giga, and so on. Exponential powers can be used, like you do centimeter square and so on. There are so many textbooks that they refer to that, perhaps the statics textbook that you have. I don't know whether it's Merriam or other textbooks. They would definitely have a chapter allocated to this section. So you always have to when you use this one, you have to respect to the dimensions. They should have both sides the same. So for example, a distance is equal to speed multiplied by time. Why? Because the speed is distance divided by time. You multiply speed divided by speed, which is distance divided by time, multiplied by time, then the time will cancel each other's and you get the distance. If the dimensions both sides are not the same, definitely there is a mistake. So it should always dealing with the same dimension both sides of an equation. Always use appropriate number of the figures. I recommend students for final answer 3 significant figures or decimal would be fine. For interim calculation, I suggest 4 decimals. Why? Let me give you an example. The biggest airplane, passenger airplane made, it's the Airbus A380, and it's luxurious. You know, they have, it's so huge that they have also very kind of presidential suite inside. You can just sleep in the airplane. You know, the name it's called presidential suite, but it costs about $30,000, $40,000 to go over seas. But let's get back to the point. So the weight of this gigantic airplane is 4.21 10 to the power 5 kilograms. So this is huge. It's 4.21 10 to the power 2 tons. It's 421 tons of steels. Why not we have to round this to two significant figures? Because if we do, we are missing 1,000 kilograms, a ton. So a ton is huge when you sending something to the air. And if you go out of space, every gram counts. So it depends on the sensitivity of your calculation. That's why you have to always respect significant figures. Again, we talk about the rounding rules. Perhaps you can go over previous chapters. Let's have a kind of attention quiz. So for a statics problem, your calculation shows the final answer as 1, 2, 3, 4, 5.6. What will you write as the final answer in kilonewton? So let's just look at here. So you have this answer in Newton. So 1, 2, 3, 4, 5, 6 significant figures. So now you want to write this one in kilonewtons. So obviously in kilonewtons, you know, you have to use the same significant figures. So the answer is this, except the fact that there is a 5 missing if you pay attention. So we have to go by the same. Maybe you can add a 5 here. This question I will answer it later. To the next. Question number 1. For a statics problem, your calculation shows the final answer is 1, 2, 3, 4, 5.6 Newton. What is the answer, the final answer in kilonewtons? Remember, the rule of thumb is we keep the same significant figures. So this obviously has 6 significant figures. If you want to convert that to kilonewton, you have to divide it by 1,000. Having said that, then you have to have same significant figures. Obviously, this is incorrect. This and the other ones, this is completely incorrect because the number is incorrect. So you know that you divide this one by 1,000 should be 12 point something. So this is incorrect, and this is obviously incorrect. So between these three, this has only 3 significant figures, this has 2 significant figures, this is the only value has the same number of significant figures as your answer. So this is correct. I will talk about it a little later, but I just want to see if you have heard about this concept. So I always tell the students when they start to deal with a problem, you think about IPE. So IPE stands for 3 words that you should implement during solving the problems. What does P stand for? So in this case, P stands for to plan. So you have to plan. We will cover this in a few minutes. The students often ask about the gravity and how do we get this number of 9.81, where it's coming from. Well, let me just shed some light on this. The whole thing is from a simple formula. This is the universal formula of 2 objects when they are in a distance from each other. They attract each other, especially when you have a huge object like Earth. So the formula is the force that these two attract, which is equal to each other is G, capital G, M1 multiplied by M2 divided by R square. So G is a constant, which is 6.6710 to the minus 11 Newton meter square, kilogram square. And so the rest of these two, let's say one is the earth because the gravity, and one is the object. For example, an apple. So you using this simple W called mg, and you want to calculate the acceleration. So you want to find this g, so g is equal to W divided by m, and m is obviously the mass of that object. So you put in the equation, two of the m cancel each other, this m and this m cancel because both refers to the object. The other m1 is the weight of the earth. So the answer become gm r square. So g is this value, g is this value, as we talk about right here, and this is the mass of the earth, and this is the radius of the earth. So it's from here to here. If the object is a little further, 10 centimeter or a meter, it's very insignificant compared with the radius of the earth. Needless to say that if you go very far, if you go a kilometer distance from the earth, the g will definitely change because this will become this number plus 1000. So simply you follow this calculation and you get the famous 9.8 or 9.81, which is the gravity acceleration. This is what actually we were talking also, if you recall. So if you go a distance of h above the surface of the earth, g will changes, and you can see that g becomes smaller because this value is more than this value. So but for small distances, 5 meter, 100 meter, 200 meters, it's very insignificant, and the g technically remains the same. So this is what I wanted to talk about IPE when you deal with solving a problem. When you see a problem, no matter what problem is this, even non-academic, first thing you should do, you should try to interpret the problem, identify the problem. In the framework of academic, you read it, you understand it, you try to get all the information, you try to make all the assumptions. This is the most important part. Often students miss a very detailed information, and that's why they cannot solve the problem. Read, interpret, find, ask, see what are the assumptions. I think you should spend quite a bit of time on this part to identify the problem. The next is you plan. You should have a plan how we get, these are given, this is what is asked. What is your roadmap? What is your strategy? This is the plan that you have to have. And of course, having a plan is good, but only it works when you execute the plan, when you do it. So don't forget about these 3 letters. When you see a problem, you're giving a problem. So in order to solve it, yes, we have to read it first. Then you have to identify a plan, a roadmap, and then we have to execute the plan. This would be the end of this module.